fourth unit. Okay? And the fourth unit is canonical transformation and Poisson bracket. So, if you have seen any of your previous year competitive exam question, be it GATE or NET, they do give you question from canonical transformation and Poisson bracket. Okay, so both are actually very important. But then, as always, I would like to I prefer teaching you from the basics so that we can actually proceed to these more advanced technical terms in classical mechanics. Okay, so it's not very complicated. It's actually we are dealing with a function, okay, in certain way, so that things becomes a bit more easy for us. We understand whether the system is conserved or not. Okay, we have more information about the system, just like we have seen in Hamiltonian. So what happened usually was that till now, the terms that we are going to use again in this chapter is configuration space and phase space. So we did see that if we are considering something as configuration space, it means that we are just considering the XYZ coordinates, okay, or R theta coordinates, okay, be it spherical or polar or Cartesian coordinate. But then if you want to find out the momentum, we have to also consider it in phase space. So that's very important. But then if you consider phase space, it gives us more information. Okay? You also know about the path of the particle, movement of it, and so on. So that is why we are actually going to continue with that. Okay, that's important. So the first thing is, what do I exactly mean by transformation? Okay, so whenever you are actually going from one system of coordinates to another system of coordinates, okay, we usually do that as per our convenience. If we are able to reduce some coordinates, if we are able to do some calculation more easily, we do it as that way. Okay, that is actually everything, nothing but a part of transformation. Okay, so if you consider any system, it basically can be represented by more than one set of generalized coordinates. Okay, what do I mean by that? You can consider a Cartesian system, you can consider a polar system. Okay, and you can always shift from one system to another. Okay, so what we do is we actually choose it based on our convenience. Okay, so we choose a convenient set. So that is the beginning of transformation. Okay, and then this also happens that if we are, let's say, finding out the equation of motion and we write down the Hamiltonian of a system, we do observe a number of times that theta, which is actually a part of the polar coordinate, will be cyclic. Okay, so that means it is not appearing, okay, there in the Hamiltonian or in the equation of motion that we're talking about. That's cyclic. Okay, but then if you write it down in terms of x and y, they are not cyclic. Okay, are not cyclic. Sorry, are not cyclic. So x and y might not be cyclic, but theta will be cyclic. So if I want to write down an equation and do our calculation in terms of x and y, the calculation might be longer compared to the calculation when we do it in terms of theta. Okay, so what happens is when you're considering a polar coordinate, you basically have only r that appears in the Hamiltonian. R appears in the Hamiltonian. Okay, so that's very important. So what we need is, we basically need a procedure to transform from one system of coordinate to another. So if I want to transform from the Cartesian coordinate to the polar coordinate, I basically need to do some mathematical steps, right? That is what we do. Okay, so if we remember your high school, okay, when you actually write down r, okay, which is nothing but the position coordinate of a point. So that position coordinate can be represented in terms of x and y, okay, x and y. And then if you want to consider a system of coordinates, and if you join this point from here, this will be actually representing r, right? And you can always write it down in terms of x and y, because this is y, okay, and this is x. So you can always take this Pythagoras theorem, and then r square is x square plus y square, and do your calculation. So we know that we are actually transforming from one system to another. Okay, so that is basically called the transformation. Okay, similarly, you can also write down theta. So theta is equal to nothing but tan inverse of y by x. Okay, so that trigonometry part, it's easy. So theta is also a function of x and y. R is also a function of x and y. But when we write down an equation in terms of r and theta, there are chances that certain coordinates will not appear. Okay, so we do see it mathematically. Okay, and that's the beauty of transformation. We can always do a calculation in much easier steps. Okay, so that's the basic that we need to know before we actually can start off with this unit. Okay, so there are two main terms that we need to start off. what is point transformation and what is canonical transformation. So herein comes the concept of configuration space and phase space. Okay, so I'll just give you one single word here so that you can remember, all of you, what is point transformation. When we are talking about point transformation, we are just considering the configuration space. Okay, so we are just concerned about the configuration space. Okay, but then when we are talking about canonical transformation, that means we have to include momentum. So that means we are going to talk about the phase space in this case. So this is actually the fundamental difference between point transformation and canonical transformation. Okay, so if we just proceed with that, okay, let's just go with the definition, okay, the bookish definition that we should know. Point transformation, we have basically it happens actually, it's actually a transformation where you're changing from one set of coordinates to another set of coordinates. Okay, so you basically, let's say you have a function in terms of only qj, you transform into a new set, capital Qj. So please remember, there is a difference between this small qj and this capital Qj. Okay, so that is there. So you can actually write down the function in this way. This capital Qj is nothing but a function of small qj and time. Okay, so this qj, if it's written in the form of an equation, will have a small qj component and t. So t is time, and small qj still remains the generalized coordinate that we have studied about. Okay, so this is basically called a point transformation. It's simple, right? We don't have any kind of momentum here. Once we include momentum, it becomes canonical transformation. Okay, so what happens here is that this transformation, that means point transformation, only gives info on the position, okay, and not on the velocity. You know, no momentum is involved, so I don't know anything about the velocity here. But then what happens is, if we just want to put it in one single line, point transformations are the transformation of configuration space. So if you remember, configuration space, right, x, y, z, right, and then how does it differ from phase space? It is phase space, we have got x, y, and z. Okay, and then we have got px, py, pz, px, okay, py, and pz. So we have some additional information that we can actually derive from phase space. Okay, so if this is clear, we can just get back to this, and then let's talk about canonical transformation. Okay, so canonical transformation. Okay, so the idea is simple. Canonical transformation. So what are canonical transformation? Are basically transformation of phase space. That's it. Okay, and we have information about both momentum and position. Okay, and what is the property of such transformation? Such transformation leaves the form of Hamiltonian's equation of motion invariant. Okay, so there is a very important difference between invariant and covariant. I've written it by the side, but I have to rotate it. So I'll just probably rotate this view so that all of us can read it. Okay. Okay. So read this covariant. So before we go into the term, let's just read what is covariant and what is invariant. Okay. So you'll come across these two terms again and again. What is covariant and what is invariant? Okay. So if you basically have an equation and it is being true in one system, okay. So you have an equation and it is true in one system. Let's say it is true in the Cartesian system, okay. Then it must be true in every coordinate system. So that should also be true in the polar coordinate system. And if it is not true, this is actually not covariant. But there are certain physical phenomena where it does happen, that if you change the coordinate system, it's not true for the other coordinate system. Okay, the equation kind of changes. So these are not covariant in nature. Okay, so you have to understand what is covariant. If an equation is true in Cartesian coordinate, this will also be true in the polar coordinate. Okay, so if an equation is true in one system, it will also be true in the another system. So that is covariant. Okay, and what do you mean by invariant? Now, invariant is slightly different from covariant. The equation form remains the same. Okay, so what happens is exactly same form of equation in every coordinate system. So even the form of the equation remains the same, doesn't change. Okay, and that's the main difference between covariant and invariant. Okay, I think that is important. So we will just keep this in mind. Okay, and then we can actually just get back. Okay, so I should rotate right. Okay. So once you know what is covariant and invariant, okay, we can just go back to this. Such transformation, okay, leave the form of Hamilton's equation of motion invariant. So that means the form of the equation does not change. Okay, so that is very important. So the form of the equation will not change. Okay, and that's what is canonical transformation is all about. Okay, and let's talk about the Lagrange's equation. Now these Lagrange's equation are covariant with respect to point transformation. They are covariant, not invariant. Okay, so it is basically true for both the systems. Okay, but the form of the equation might not be same. Okay, so that is important. So ddt of del L del Qj dot minus del L del Qj is equal to 0. So if you basically remember what you did in the coordinate system that we're talking about in terms of generalized coordinate, we wrote it as q dot, okay, small q. Now here we are actually representing it by small capital Q dot, because this capital Qj dot is nothing but the transformation that is happening. Okay, we are going from Qj system, okay, to capital Qj system. Capital Qj. Slowly it will be clear why we are doing it. Okay, we definitely have an important intention behind doing this. Okay, so we have got the Lagrange's equation, and Lagrange's equation form will remain definitely the same. Okay, so that is very important. Okay, next we have got the Hamiltonian. Okay, so if you basically consider the Hamiltonian, um, the momentum is actually one of the variables. That is one of the fundamental difference that we know between Lagrangian and Hamiltonian, right? So momentum is one of the variable. So whenever you are basically considering any equation, let's say the Hamiltonian equation, we have to have a transformation if we are considering it in this chapter. Okay, so there has to be a transformation. So basically when we talk about let's say generalized coordinate as qj and generalized momentum as pj, we are transforming from one set of coordinate to another set of coordinates. See, this is a general form. Okay, this is a general form. I'm not really saying that I'm transferring from a Cartesian coordinate to a cylindrical coordinate, or Cartesian coordinate to a polar coordinate, and so on. I'm not saying that. We are just generalizing the case. Okay, as we have seen in the last 3 units, that every time classical mechanics talks more about a general outview, and that is very important. Okay, once you know the general picture, you can always implement it to study specific cases, and that is why generalization is important. So we are saying that this momentum is changing to capital PJ, and this generalized coordinate will change to capital QJ. Okay, so whatever we represented with Hamiltonian and Lagrangian, everything was written in small. Yeah, everything will be written in caps. Okay, so in all capital. So we have got this capital QJ. Capital QJ is again no doubt a function of Q, P, and T. Okay, and then this PJ is also a function of Q, P, and T. So this is a very important thing to remember. Okay, and this is something which we reached at analytically. We use some logic and tried to say that okay, we're transferring from one coordinate system to another coordinate system. Okay, and we are representing small qj, but we have capital qj now because we are going from small qj to capital qj. Or let's say, for example, we are transferring from the Cartesian to the polar coordinate. So any kind of idea you can think about, and then that the picture will be clear. Okay, let's look into the Hamiltonian equation now. What happens to the Hamilton's equation of motion? So originally Hamilton's equation has the form this: qj dot is equal to del h del pj, and pj dot is equal to minus del h del qj. Okay, so you know we said that we have transferred to a new set of coordinates, so we'll just replace this small qj and capital qj by capital qj and capital qj. So this is our new set of coordinates. Okay, so you understand this, the approach has not changed much. Okay, we are still with Hamiltonian and Lagrangian, but then we are looking into it from a point of view when we are actually going to change the coordinate from one system to another. So we're just going to replace it. Okay, and this more or less remains the same. So the question is, will you be confused in exam? The answer is no, because it will be specifically mentioned. Okay, so you don't worry. I'll show you some questions which you will easily be able to catch up, whether you have to write it down in terms of small qj or capital qj as we proceed to the chapter. But then this is Hamiltonian, this is small capital H. Okay, and this Hamiltonian which we talked about initially was a function of small qj, okay, small pj and p. But now, since we're talking about capital Qj and capital Pj, this Hamiltonian representation should also change. So what we do is we usually represent it by a variable k. Okay, we can write it down as capital K. So this caps k is basically a function of capital Q, capital P, and capital T. Okay, so this is not fundamental. Okay, it's like it can be derived in other sets of units also. Okay, so this k is a substitute for the Hamiltonian. So that's very important. So once this is clear, we are actually revisiting all the old equation, and we are just transferring from one set of coordinates to another set of coordinates. Okay, and then if you please remember this Jacobi integral. Okay, summation pj qj dot. Okay, it's there. So we do have this capital Qj and capital Pj as the canonical coordinates now. Okay, and they should also satisfy the Hamilton's principle. Okay, it should also satisfy the Hamilton's principle. So here when we talked about this, okay, this was our equation original, where was h, now it is k. So whenever there is a k, we are more or less relating it with h or l also. Okay, similar. So this should be invariant. Okay, so if we talk about a delta and then integration of t1 to t2 summation j, if you remember, pj q dot minus l is equal to 0 was the answer. Okay, it is also applicable for Hamiltonian because this is nothing but talking about the invariance. Okay, so there is not much of a change. Okay, whenever going from one point to another, and you're talking about the kinetic energy and potential energy. So if you don't remember that, you have to definitely look into the Jacobi integral where I've explained this fact. So I'm not explaining the what is Jacobi integral. I'm just replacing the variables here. Pj capital Qj dot minus k, q, p, and t. Okay, and dt is equal to 0. So this is one more equation that is there. Okay. So in today's class, I'm not really telling you to learn something new. We are just transferring from one coordinate system to another coordinate system. Okay, and then we will see what can be applied here. Okay. So in Hamilton's principle, if you're basically considering this delta and this is L dt, okay, this L, if you replace by h, still it is valid. Okay, so please don't get confused that it was L here and k is a replacement of h and not L. Why does k come here? Okay, so even if you use a h here, this is still invariant. Okay, because this also contains kinetic energy and potential energy. Okay, so don't get confused here. So what we do is summation pj qj dot minus L is this. Okay, but anyway, this one I put it inside bracket so that you can recall what was Hamilton's principle. Okay, so that was our Hamilton's principle, if you remember. Okay, so this is important. Okay, and this is the very much the beginning. Okay, and then I think this is very much basic, so I'm not going very slow, I'm going a bit fast. So in terms of the old coordinates, if you want to write it down, you will always write it down as small pj small qj dot minus h, which is a function of small q, small p, and time dt is equal to 0. Okay, and then I think this is also very obvious that if this right hand side is 0, okay, if this part is 0, okay, it definitely does not imply that the integrands of two integrals are equal. Okay, it's definitely not true, right? If you take this part and you take this part, okay, it doesn't mean that if you integrate this and integrate this, they will be equal, so that when you subtract this from this, it will become 0. That's not true mathematically, right? So we understand that fact. Okay, and then what we can do is we can just separate this out. Okay, so we can just separate this out. So summation pj qj dot minus h. Okay, that was in terms of the new coordinate, old coordinate system, and then capital pj qj dot minus k is equal to nothing but in the terms of the new coordinate system. Okay, so this is also true. So that means this also is a special case of Hamilton's principle. Okay, so that is again important. Okay, and then what we can do is we can actually consider another variable. See, we are changing all sets. Okay, another variable. So let's say that variable is f, and then you will know slowly that this f is called the generating function. And this is a very important part and one of the most favorite topics of the questions which are being put on for net exam or gate exam. Okay, so this f is basically a function of small q, small p, and t, let's say. Okay, we are just saying it, but we are considering this. So we can simply write it down as del f dt into dt is equal to delta of f qpt t1 to t2, right? You have to basically do an integration here from t1 to t2. Okay, and this delta of df. Okay, so you see dt will get cancelled out here, you've just taken a delta of df. So integration of df would be f. Delta is already there, and then you're integrating it from t1 to t2. Okay, so that's basically differentiation that you're doing, right? And then if you want to write it down in terms of t1 and t2, you can always write it down as delta f delta qj into Kronecker delta qj, right? Basically call it as Kronecker delta, and then delta f delta pj into Kronecker delta pj t1 to t2. Okay, so the question is this will actually become equal to 0. Okay, this will become equal to 0, and of course the question is how. Okay, how does it become equal to 0? Okay, so what happens is if we are going from t1 to t2, that means you are considering the variable from one end to the other end. And whenever you write it down in terms of small delta, that means you are considering the variation. Okay, so the case is such that at these two extreme points, T1 and T2, there is no variation in Pj, and then there is no variation in Qj. There is no variation as such. Okay, so what happens is at the end points, the variation in Qj and Pj will vanish. Okay, so at the end points, they more or less will be at the same point. There won't be any much variation in the coordinate system. There won't be any variation in the momentum. Okay, now the question is, why did I do this? Because I will be using it in the later case. Okay, so what I'd like is that I'd like to stop here, because then if I continue with this, I have to go to generating function. Okay, but then I think I can just go explain you this. I think this is okay. Yeah, so let's take this delta of this minus this, okay, which you have already done. Okay, and then I can use this additional term df dt. So delta minus df dt into dt. This is the additional term that I'm using. This is the additional term that I'm using. But I can use it. Why? Because this is 0. Just now we have seen that at the end point, since there is no variation, this part is actually 0. So if I add or subtract 0 from this equation, it doesn't make a difference to the final answer, right? So you can always put it there. If you do that, what we can do is we can add df by dt, right? And if we do this, what we can say is that this part will actually be 0. Okay, and we have got delta of integration of t1 to t2 in this minus df into dt is equal to 0. Okay, and this minus this must be equal to this, and then only this integral will be 0. As I said, that these two integrals separately cannot be 0, might not be 0. It's not mandatory, because as I said that they have this covariance. Okay, they have this covariance. So the form of the equation might be different. So if you integrate it, it's not necessary that this and this will give you 0. Okay, but then if this is the variable, and if these two, okay, understand it mathematically, if these two becomes equal to df by dt, okay, becomes equal to df by dt. df by dt is not 0. Integration of t1, t2, delta is there, and then dt, then it's 0. df dt is not 0. Please remember this, okay? df dt is not 0. So that means if this part becomes equal to this part, then only I can say this entire integral will become 0. Okay, in simple words, I have to find out what should be the form of this entire part. And for that, I have to represent it in the form of some equation. And that is why we are writing down this part. This is where we start with generating function in the next class. Okay.